Okay, so check this out. In the last video, we talked about compounding interest. And the more often we compound, the more interest we're going to get, right? Because we're going to be paying interest on more and more interest. But here's a cool thing. The cool thing is, if the number of times we actually compound get really, really big, we don't actually end up with the amount that we have to pay getting bigger and bigger and bigger and bigger. So that by compounding every nanosecond or something, we could have to pay as much interest as you can possibly imagine. Let's see what happens, and I'm going to see what happens with some really simple numbers, simplest possible numbers. Let's see what happens in that compounding formula if I let r, t, and p0 all be 1. So the only number I'm really interested in is n. Right, when n is 1, I know what I'm going to get, but I'm just getting in the habit of putting this into the calculator. I get 2. When n is 2, I get 2 1/4. Okay. Let's skip on a little bit. What if we're compounding every month? What if n is 12? I get about 2.61. What if we're compounding every day? 365 days in a year. I get about 2.71. Okay, now I'm going to stop thinking about this as some fixed time period. I don't know how many minutes there are in a year. So let's try just 10,000. About 2.72. What if I make it even bigger? Just going to go back in here and add an extra 0 to both of these numbers. So now I've got 100,000. That didn't change very much at all. Right, it changed in this place. What if I add even another 0? Okay, that changed in one more place. Let's try one more 0, and after that I think my calculator is probably going to start to complain. That didn't change very much at all. This is going to get closer and closer to, well, some number. There's some number that's the cap on this. And that number is one of those numbers that's not rational. It's not a terminating decimal. It's not a repeating decimal. But it comes up in a lot of places. So we give it a name. We call it e. My calculator has a button to take e to some power. I'm just going to take it to the first power. And see here. This looks a lot like those numbers that we kept getting as the results of those computations. So we write e, and e is called Euler's number. It's spelled this way. It's pronounced Euler. Euler is a person's name. It's a mathematician. It's about 2.718281828. Where did I get that? This is what my calculator gives for e. If you ever have to come up with it, 2.72 is a pretty good approximation. That's kind of like saying pi is about 3.14, when in fact pi is another number that just keeps going forever without repeating itself. And it turns out that this number comes up frequently, just like pi does. And it turns out to have some really nice properties for doing calculus too. Those properties are so nice that we give the log base e its own name. We call it the natural logarithm. And we write ln. And I usually write ln in cursive so that I know I didn't write 1n. That's not required, but remember, that's the letter L, not the number 1. One of the main reasons we bring this up at this point, other than so that when you see it again you'll have seen it before, your calculator has a log button. It also has a natural log button. And notice the second function of this natural log button is e to the x. So, let's see what we can do about this. We could just use the calculator to find e to the 11. Right, hitting second and then that ln key gives me an e to the, I put in 11. Rounded to 3 decimal places, that's going to be about 59,874.14. ln 12, putting that into the calculator, I hit ln and type in 12. That's about 2.485. And to check that, remember the ln is the log base e. So we can rewrite that as the base stays the same. 2.485 is the result of the log, so it becomes the exponent. E to the 2.485. That's pretty close to 12. I'm going to give you a couple of these to try just to practice using your calculator. Again, round all your answers to 3 decimal places. So find e to the 1/2, then find the natural log of 0.6, and check by writing an exponential notation. Pause the video and try this now. Okay, well, e to the 1/2, we'll get about 1.649. ln 0.6, we'll get about negative 0.511. And then checking that by writing an exponential notation, e to the negative 0.511, yeah, that's pretty close to 0.6.